In this video, we're going to look at another example of a situation where we can do a backwards U substitution where we use the form of the integrand to give us a hint for what is a good substitution to do. So here's the example we're going to work with. It's the integral of x times the integral, the integral of x times the square root of x squared plus 4 dx. So like the last example, there's an inside part with a square in it that might make you think of a Pythagorean identity for trigonometric functions, something like sine squared theta plus cosine squared theta equals 1. Except in this Pythagorean identity, there are sort of two squared variable parts on the same side with a plus in between. But in our integrand, we don't have two squared variable parts. One part is a constant. So maybe what we should do is try to think of a Pythagorean identity that has plus a constant on one side, and you might remember this one. If you don't, that's okay, I'm going to remind you. So tangent squared theta plus 1 equals secant squared theta. This second Pythagorean identity comes from the first one just by dividing everything by cosine squared. So in this Pythagorean identity, we have a variable part squared plus a constant equals something nice, something squared. Right? This square on the secant, that's going to play nicely with the square root in our integrand. So what this is inspiring us to choose for x is tangent. But actually, this 4 here, it would be nice if it were a 1, right? Because we have x squared plus 4. If x is just tangent, this will be tangent squared plus 4. So it would be nice if that 4 was a 1. Well, if we put a 2 right here, which is the square root of 4, then when we square 2 tangent theta, we'll get 4 tangent squared theta, and then we'll have a 4 that we could factor out. Okay, so this 4 right here is causing us to multiply our tangent by 2. Okay, before we actually do the substitution, we have to figure out what dx is. So 2 times derivative of tangent, that's secant squared theta d theta. And now we're ready to do our substitution. So this is the integral of x is 2 tangent theta, and then this square root is now the square root of x squared is 4 tangent theta plus 4, and dx is 2 secant squared theta d theta. Okay, so there's kind of a big mess here. Let's see what we get. Let's see, there's two factors of 2 in this integrand, so let's pull those both out. We have 4 times the integral of tangent theta. The stuff inside the square root is, if you factor out the common factor of 4 here, and then pull the 4 outside the square root, it becomes 2 times the square root of tangent squared theta plus 1. We took care of the factor of 2 in front of secant squared, so that leaves secant squared theta d theta. All right. Things are starting to look up because now we can use our Pythagorean identity. We have one more factor of 2 to pull to the outside, so that makes it 8. 8 times the integral of tangent theta times. Now for the Pythagorean identity. The stuff inside is secant squared theta, and the square root of secant squared is secant. Well, really it's the absolute value of secant, but you can't integrate across the discontinuities of secant anyway, and so one continuous part of the graph of secant is always positive if we choose the right part. Okay, so subject to some domain issues, we can just put secant theta here. Okay, and then the secant squared from before, secant squared theta d theta. And now combining all of our powers, we have 8 times the integral of tangent theta times secant cubed theta d theta. Now we have to figure out how to evaluate this integral. It's not especially nice, but you know, the powers of secant make me wonder if a u substitution would be a good idea. So now I'm on the lookout for the derivative of secant. But the derivative of secant is tangent times secant. And that leaves a secant squared theta. I now realize I've essentially undone the simplifying that I did before, so maybe we should have kept this previous step up here. Anyway, now we can do a u substitution. If we let u be secant theta, then du is tangent theta secant theta. Oops, tangent theta secant theta d theta. And now we can rewrite this integral. This is 8 times the integral of, so tangent theta secant theta together with d theta make du. And then secant squared is u squared. Oops, this should du. Okay, so now finally we can do the integral. It's 8/3 u cubed, plus a constant, of course. But wait, this is an indefinite integral. For indefinite integrals, you need to get back to the original variable so that you have a function of the original variable. So we need to undo our u substitution. And we have to undo our backwards u substitution, the trigonometric substitution that we originally did. So let's see how that works out. So we have 8/3 u cubed plus c. Let's copy that over to a new screen up here. So we have 8/3 u cubed plus c. And remember, we did two substitutions. On the one hand, u was secant theta, and on the other hand, x was tangent theta. Sorry, no, x was 2 times tangent theta. Okay, so 8/3 times u is secant, so secant cubed theta plus c. And now somehow we need to rewrite secant theta in terms of x. To do that, let's write the power separately. So 8/3 times secant theta cubed plus c. So what we need to do is figure out, how do we turn secant theta into x? Okay, well, here's one way to do that. If we take this substitution equation, solve it for tangent theta, we get x over 2 equals tangent theta. Okay, but we need to get secant theta into the game here. Well, actually, let's do it this way. So tangent theta, that should be opposite over adjacent, right? So if we draw a right triangle and we put the angle theta in this lower side here, to make tangent of theta be x over 2, we need an x on the opposite side and a 2 on the adjacent side. And then we can use the Pythagorean theorem to find the hypotenuse. It is the square root of x squared plus 2 squared, which is 4. Okay, and now we can use this right triangle to express secant theta. So this is 8/3 times secant theta. And in this triangle, secant is hypotenuse over adjacent. So 1/2 square root of x squared plus 4. So that all cubed plus c. And now to finish it off, we can do a little bit of simplifying. This 1/2 right here, when we cube it, 1/2 cubed is 1/8, and that's going to cancel the 1/8 in front, so we get 1/3 times x squared plus 4, square root to the third, so that's to the 3/2, plus c. So there's another situation where the form of the integrand inspires us to choose a certain trigonometric substitution. So if we have a sum of squares inside a square root, we can often use tangent, do this tangent substitution to make progress on the antiderivative. There's one more situation where a trigonometric substitution is a good idea, and we will look at that one next.